Welcome to the Local Nature Rock Beneath Your Feet event. My name is Molly Clemens. I'm an outreach student assistant at the Center for Environmental Inquiry. Our public events are usually done either at the Osborne Preserve on the Sonoma Mountain, in Pengrove or in Gilbert Preserve near Yorkville and Mendocino. But for the 2020 and 2021 school year, all of our events are virtual. We're excited to help you connect to nature and learn how you can make a difference even during a pandemic. Can everyone please take a moment to type out their full name into the chat box? This is our sign-in sheet. Thank you. Before I let Nicole Myers take it away, I want to tell you a little bit about what the Center for Environmental Inquiry is and how we can be a resource for you, no matter if you're affiliated with the SSU or not, or whether you're a student, parent, government employee, educator, and member of the public, or an organization in need of environmental solutions. The center envisions the North Bay working together to find environmental solutions and invites you to get environmentally ready with us. We're building a community of learners and problem solvers across all sectors of society by providing firsthand understanding of our connections with the environment, skill building experience that results in sustainable solutions, and there's many ways to get involved. You can be a part of the virtual field collaboration, joint internships, student jobs, and access to data and lead events like these. And partner with us on other projects. You are important in addressing the greatest environmental challenges in history, as witnessed by the recent wildfires. A diverse, engaged society is critical. Today, we're going to focus on the link between Today, we're going to focus on the geography and the environment, in the geological history with our professor, Nicole Myers, with Sonoma State's professor, Nicole Myers. This is one of our local nature events, which combines a live presentation with exploration of the natural areas right around your home. So today we'll spend about a couple minutes hearing from Nicole and then connecting to our local nature areas using the Rock app that we'll have some time today to learn and how to use. We're happy to stay a few minutes for more of this, and feel free to email me after this event for any follow-ups. Nicole would love to see your faces for the video. Your faces on your video are all, but please keep your sound muted unless you have something to add or ask to minimize the background noise. If you need anything earlier, feel free to type in the chat window, like if you can't see or hear Nicole. Please use the chat feature during the Q&A portion at the end of the event. And I'll read the questions out loud for Nicole to answer. All right. I think Nicole can take it away and tell us a little bit more about the geological process.
Thank you, Molly. That was awesome. I'm really excited to be here today because I found the coolest app, but I think many of you might already know that I'm a complete rock nerd, so my idea of cool, I hope you agree with. I am going to be focusing on how you can use this app called Rocked to understand the rocks beneath your feet. Yes, geologists love bad puns. We can't help it, it's gonna happen. If you haven't already typed your name in the chat box, and then just add like #1 if you learned about this event through the Center for Environmental Inquiry emails, or even their website. 2, for if you found out by social media. 3, if you found out through my newsletter. 4, if you happen to be one of my geology students this semester, or 5, if there's another. We love to find out how you are hearing about these kinds of events. I'm going to spend the first part of this talk actually like going over the information, background information you need to be able to use this app, how to interpret the information. I have provided instructions on my website. I added this website to the chat, so it's at the very, very top of the chat. And I've also added this website, which is rocked.com, the source of the app. This is what that website looks like, into the chat so that you can get to that easily as well. And there will be time for questions at the end, I promise. I'll make sure there's time. Now, for those of you who have already played with geologic maps, you know that they are intense. There's just a lot of information on a geologic map. And every geologic map is different. So what the Rocked app does is it puts this information at your fingertips and allows you to zoom into your current location and be able to discover the geologic information about that specific location and the adjacent regions, which is great because, as I will show you today, geologic maps are completely overwhelming, and the attempt to find where you are on a geologic map has caused many geology students to throw down their papers and walk down the hill. It has happened. So one of the things that we want to focus on today is really just understanding the very basics of a geologic map. We have colors, as you can see. It kind of looks like a watercolor painting on here. When you see the color yellow in multiple places, that means that is representing one kind of rock or sediment that is forming in a specific manner. So each color represents a different rock or suite of rocks and the environment in which they're forming. So think of every color as like the color code, an indicator. And then the patterns, those are telling us more about processes, like how did those rocks get there? How did they form? When we see these black lines that are oriented northwest to southeast, from the top left to the bottom right, that gives us a sense of how the rocks got there and how they're moving, which is really about tectonics. I'm going to start with patterns today, and then I'm going to come back to rocks, and then we'll go to the app towards the end. Now, as I saw from the early sign-ins for this talk, the vast, vast, vast majority of the people, in fact, everyone who signed up early, is on the West Coast of the US. We have everyone from Washington all the way down to San Diego. And if you signed up a little bit later and you are not on the West Coast, then throw that in the chat so that I know to cover that area at least a little bit during my talk. And Molly, if someone throws something in the chat about not being in Oregon, Washington, or California, definitely let me know. One of the things about California is that it is really complex. I actually feel bad for geology students who have to learn about geology in California because it's the most complex. Every kind of rock is here and every kind of tectonic boundary is here. There are 3 types of tectonic boundaries. Now, the surface of the Earth is actually broken, like think of it as a shell that's broken into plates or pieces. And then those pieces are moving relative to each other. So there's 3 ways in which those pieces come together and meet and move relative to each other. And we call those tectonic boundaries. Now, a divergent boundary is where 2 plates move apart from each other. And you'll see this in the video here. I'll kind of be doing segments of the video at a time, but you can see the hot rock from below is rising, splitting in 2, moving apart and dragging the plates apart with it. That is a divergent boundary. When we think of a divergent boundary, essentially we're looking at how ocean crust forms. It's literally the birthplace of the entire floor of the ocean, which is 70% of our planet. So that's significant. It is entirely volcanic in its process. So it's made out of volcanic or what we call igneous rocks. And then those rocks are carried through that tectonic process, the movement of the surface of the Earth to new locations. So we actually have two kinds of tectonic, or I should say divergent tectonic locations within the West Coast. I'm going to start first with California. So if we think of the San Andreas Fault portion of California, we end up having what we call ophiolites. Now, ophiolite is just a fancy word for chunk of ocean floor. Yes, in geology, we have 1,000 terms you've probably never heard and will never hear again. It just means chunk of ocean floor. And I want to note is that right underneath the Great Valley, that's what geologists call it. Everyone else calls it the Central Valley, but it's great to geologists. And we can see beneath it is this chunk of ophiolite. This is literally a chunk of the ocean floor that snapped off and got stuck on the edge of the continent, which is amazing. Now, that's not the only place we have divergence occurring along the West Coast, or this pulling apart. It actually is also forming down here. This is where our Gulf of California is. And here we have Baja, which is moving away from mainland Mexico. And this technically extends all the way up to the Salton Sea. And this pulling apart is shoving San Diego to the west and the eastern portion of California to the east. It's creating those mountains. So that's part of the reason for the geology that's happening in the south. That pulling apart action is happening throughout even Death Valley areas. The second part, or I should say second type of boundary, are convergent boundaries. They're coming together, and we can see that here. The coming together of two plates is always going to be destructive. Whenever two things try to occupy the same place, it's generally going to be destructive. It doesn't seem to matter where that happens. It's just a law of nature. And this becomes an incredibly important part of the story of the West Coast, because not only is this process occurring right now for the northernmost part of California, all the way up through Oregon, Washington, and into Canada, but this process also occurred deep into the past for the entirety of the coast. So here we have our little Juan de Fuca plate. Now, the Juan de Fuca plate, I'm just going to give you kind of a little background on it. It is a remnant, a leftover piece of the once great Farallon plate. It is subducting underneath. That's the plate that's going down, the North American plate, which is what our continent is upon. And these two plates are squeezing towards each other. And as they squeeze towards each other, one of them, the denser one, which is always the oceanic plate, sinks down. And one thing that I want to note here that I think is almost always overlooked in general geology, but never should be, is that this little thing here, this line we see here, we call that the trench. That's the point of meeting. And you look at this and you're like, oh, the two plates meet and one goes under. It's so like calm. No, there's nothing calm about that. All the surface rocks of that oceanic crust is getting scraped off. Think of it as like a bowl full of batter of your choice, whatever batter you like. And you take your spatula and you actually move it around the bowl and it just peels all of that batter off the bowl. That's what's happening here. So we end up with a wedge, and we call that an accretionary wedge. That is quite literally massive amounts of ocean crap that have been squished onto the edge of the adjacent plate. It is a little bit of everything. We're going to have ophiolites. We're going to have dead sea creatures and limestone and chert. There's going to be sand. There's going to be mud. It's going to be a mess of stuff, and it's going to be pretty chaotically mixed in there. And I have to note that is important because the Franciscan formation or complex, which many people have heard of, is an accretionary wedge. It's quite literally the accretionary wedge that formed over nearly 100 million years of subduction. And since then has uplifted so that you and I can walk upon it. Now that accretionary wedge is continuing to form up north off the coast of Northern California, Oregon, and Washington along that subduction zone. So we can still see this process happening in some locations today. But a convergent boundary is where ocean floor goes to die. It's going to sink down, but we get to see some of the remnants of that pretty destructive process. Now for California specifically, in a second, oops, there we go. So now you can see that convergent boundary and how it's linked to volcanoes. And we can see here in this video, I'm going to play the divergent again so you get that sense of the pulling apart and then how those plates move. And when those plates move, they come together at some point, a convergent boundary. Then you get that subduction and you consider how hot it is deep inside the earth. It's going to get hotter and hotter and hotter as you go deeper. So that plate that's being drugged down, it's going to start melting. And that process of melting is going to form, shockingly, whoa, that was weird. Shockingly, it's going to form volcanoes. So we look at this and we're like, well, Nicole, you said that this whole region that was the coast of California long ago was a subduction zone. So where are my volcanoes? You probably have already been to those volcanoes. Maybe you didn't know it. We call them the Sierra Nevadas. The Sierra Nevadas are quite literally the magma chambers, the leftover magma chambers from that once great volcanic chain. Now that volcanic chain still technically exists. It continues northward. We call it the Cascade volcanoes. It is the result of that ocean plate, the Juan de Fuca, melting on its way down. But we can also see the remnant magma chambers in the granite rocks of the Sierra Nevadas all the way down the eastern spine of California. So that's one of our pieces of evidence. We call that a batholithic pluton. Yes, we like our jargon. I just actually really like the word batholithic. It's kind of fun to say. It is. So this kind of gives us a sense of what California looked like for tens of millions of years and what Oregon and Washington still have as ongoing process. But we have one more boundary I need to cover, and that's transform boundary. Now, transform boundary is two plates sliding past each other in either the same or opposite directions. Think of it as a freeway. On a freeway, all the cars are either moving in the same direction and or the opposite direction. It's also kind of like on cars on a freeway, and I haven't been on a freeway all that often recently. You know how in the lanes, like the cars kind of jostle to and fro and you're like, too close, yikes. A little further away, much better. The same thing happens with the two plates that are moving adjacent to each other on a transform boundary. Sometimes they squish together a little bit more and form mountains. Sometimes they pull apart a little bit more and form little basins and valleys. So they're going to create a lot of range of topography. And that is what we call the San Andreas Fault System. The San Andreas Fault System is a transform boundary. That means that California, where we are specifically for the Sonoma State region, has chunks of a divergent boundary, was once a convergent boundary for millions of years and is now a transform boundary. By the way, this is not normal. If you go to the Midwest, it is a much more boring geologic story. Still has a lot of cool, interesting things happening, but not this much tectonic activity. So what a geologist does, now that we have this sense of how rocks form, what a geologist does is we walk around and we try to map it. When we have a generalized map, we essentially are going to put all the rocks that formed in similar environments into what we call physiographic regions or provinces. And what each of these zones are, which here we've given them patterns, is their common geologic origin. In other words, this is a rock forming environment. Maybe it's wet, like the ocean, or dry, like the continent, or it could be wet, like the continent in a lake or in a river. It could be volcanic. We have all kinds of words we can use to describe environments. And in every environment, different kinds of rocks are forming, which means every rock forms in a specific and unique environment. And what we're trying to do is look at those rocks and say, what environment did you form in? When did you form? And how did you get here? This is a 4.6 billion year old puzzle. It's very unlikely we'll ever actually answer all those questions for every rock, but we're gonna still try. We also need to put that in order. So we do so on the geologic timescale. I'll give you some information about that soon, because we're going to need to find a way to communicate with each other in geology about our findings. Like, what rocks have you found? What have you discovered about them? What we've discovered about California is that it was once divergent. In other words, many, many rocks formed in a marine environment when the two plates pulled apart. Then it was convergent for a really, really, really long time. So we have that process of subduction that formed the Sierra Nevada volcanic rocks. We can see that here, where we again find the term batholith. I just like saying that word. And we can see that that forms the spine of the Sierras. And we also see it scattered elsewhere throughout California because the transform boundary has made things complicated. And then we know there was this transition from convergent to transform, in which it took these oceanic rocks. And so I want to note that all of these rocks here that have this upper left to lower right diagonal, they all formed in an ocean setting. And all of these that have the opposite direction, they also all formed in an ocean setting. And then all of these that are cross-hatched are a composite of the two. And then we start to go, okay, the vast majority of California actually formed volcanically or an oceanic setting. And then it got uplifted to be part of land. So it started low and has been uplifted. The San Andreas Fault is to blame for that last bit. And the San Andreas Fault system, or the transform boundary, has done lots of faulting. Hence, when we look at this geologic map, which we'll become well acquainted with, you start to see a mess of colors. You're like, why are there so many colors? Because those faults have moved all these rocks around and made it that much more complicated for geologists to unravel the mystery. And on top of that, we need to consider ongoing evolution. Not only do the faults continue to move, but the climate continues to change. And for the last 2 million years, we've gone from glacial stage to interglacial warm stage. That's where we are now in time, back to glacier, back to interglacial. We've gone back and forth, and that's changed what kind of rocks have formed on the surface. That's what the white stuff is. The white stuff says what kind of sediments or volcanic rocks have formed very, very recently. So this geologic map on the right side, you can see here we have a key. Our geologic keys always have oldest on the bottom to youngest on the top, and that's what we're going to go into next. So here we have our San Andreas Fault system area. So you're like, okay, that's a pretty significant portion of California. Below this line that's on the bottom, that's all divergence. That's the pulling apart area. And above this line is still convergence, hence chaos. And therefore, if you are in this region and you're looking at this and you're like, I'm never going to unravel this, no one ever will. We're still going to try. But we're going to zoom in. So hopefully we're like, okay, maybe if I look a little closer, I can see details that are less overwhelming. Sorry, not going to happen. Certainly not in California in an accretionary wedge. This is just one map, and every geologic map is different because first people had to make it, and every person is different. And maps have been made over time, so what tools we have available to us and what the intent is has changed. Notice all these symbols. We call these strike and dip symbols. That's just a fancy way for geologists to say, my rock is oriented like this, versus like this, versus like this, versus like this. We have to find a way of talking to each other about how the rocks are actually geometrically oriented. That's complicated, don't worry, that's a full year of geology student speak that I'm not going to go into. What you might notice on this map is we have, once again, this pattern of stripes from northwest to southeast. You're like, okay, I can see the pattern, but if you wanted to find yourself on this map, you're like, what? Where's my GPS? I need to know where I am. The scale is also zoomed out enough that you're not going to see a lot of detail. So we start to realize, okay, we're going to need to look at a series of different maps. But before we do that, we also need to understand what each of these colors means. In other words, what kind of rocks exist? A rock, by definition, in case you didn't know, is any naturally formed, non-living, firm, and coherent aggregate of mineral matter that constitutes part of a planet. I have a lot of problems with this definition, like the word planet. I would like to know if an asteroid is therefore not a rock. And my bones happen to be made out of calcium carbonate and other ingredients that are similar to rock. So, we might need to change this definition into the future, but I will not argue that point in the moment. We have three kinds of rocks. Just like we have three types of tectonic boundaries, we have three types of rocks. We have igneous rocks. Our igneous rocks are volcanic in nature. Then we have sedimentary rocks. Those sedimentary rocks are made out of sediment or other pieces that formed on the surface of the planet and have since been transported or moved about. And then our metamorphic rocks are those formed under increased temperature and pressure. In other words, they got squished or overheated or squeezed or all of the above. So we now have three tectonic processes that are going to create, destroy, and move rocks. We have three rock types, and each rock type can become another rock type. So igneous can become sedimentary, sedimentary can become igneous, metamorphic can become sedimentary, metamorphic can become igneous, sedimentary can become igneous, or you're starting to get the idea, more chaos. So that's what the geologic timescale is. This is the geologist's way of attempting to put order to chaos, putting things in order. We now are going to say for every rock, can we figure out how old you are rock? MA means millions of years ago. So when we're trying to put a geologic timescale together, we're saying, what was the tectonic process that created this rock? What kind of rock is it? How do I describe it? How old is it? How do I put it on the geologic timescale? If at this point in time, you're like, I am overwhelmed and I will never understand anything, welcome to geology. You are paying attention. There we go. So that was my foundation of information. Let me show you pretty maps, and then we're going to get to our rocked app. This white box that I have put in place here, this designates the area of that previous geologic map I showed you with all the strike and dip symbols that still was hyper intense to look at. Here I zoomed out. So you're like, okay, zooming out didn't help. I just see a lot of colors. Our key in geology always is oldest on the bottom to youngest on the top. So you're like, okay, I'm starting to see a little bit of a color pattern. Geologists are not good with sticking with the patterns, by the way, but generally we attempt to use red and pink for igneous. And then we use kind of the greens, oranges, and yellows for sedimentary, and our darker, think of like gemstone type colors. Those tend to be metamorphic. This geologic map is a scale of 1 to 250,000. That means if you measure 1 inch on the map, and by the way, this map is like this big, it makes me into a parachute. If I hold it in the wind, it is super unwieldy and requires like multiple people to control it. It's huge. That means if I measure 1 inch on that map, that's equivalent to 250,000 inches on the ground. If I measure 1 millimeter on that graph, on that map, then it's 250,000 millimeters on the ground. So this is huge. We don't have a lot of detail, but we get to see patterns nicely. Again, unwieldy, very difficult to use in the field. So what if I zoomed in? Would that be more helpful if I looked a little closer? Now I'm at 1 to 24,000 scale. So you're like, okay, 1 inch on map equals 24,000 inches on the ground. We call this a 7.5 minute map in latitude and longitude speak. And now you're like, I thought that would help, but it didn't. But what we can see is a lot more information is provided. For every color, every rock, we get a whole paragraph of information. I'm not zooming in on it, I will in a moment. Every one of those paragraphs is so full of jargon that if you look at it, you're like, I understood 5 of those words. Totally fair. But here's what gets really helpful as we zoom in and look at a smaller area. We get to see the rocks that formed concurrently, adjacent to each other at the same time in slightly different environments. Think of, for example, Petaluma. We have the bay muds, then we have the sand of the valleys, and then we have the mountains. Those are adjacent environments. 3 different rocks are forming. So now we get a better snapshot in time. but it'd be helpful if you could see detail. So we're going to zoom in. And as we look at this detail, you're like, okay, I thought that'd be helpful. It's not. The yellow in general is the very recent stuff. So that's the sand and the mud and everything that's at the bottom of the valley. It's been placed there by rivers and landslides. And the pink is generally the igneous rocks. And this is specific to Bennett Valley, the southeast part of Santa Rosa. And I'm just going to give you a couple examples. So here I put a couple of those little paragraphs in so you can read it and be like, what? Fair enough. QLS means landslide. And you're like, I don't know if I wanted to know that. Thank you very much. There are a lot of landslides in this area, and we can see they're sourcing from the pink rock, which is our volcanic rock. Volcanic rock is pretty weak. It's going to fall apart pretty easily, and therefore it's going to start sliding downhill. QOA, I love QOA. Why? Because it used to be lakes. Every time you see QOA, that was a lake during the time of the mammoths. Like mammoths probably drank water there. And now it's completely dried up because we've been moving towards a dry climate for about 10,000 years. The rate of that drying has just accelerated. So we start to get more detail here. You're like, okay, I still don't know where I am on the map. I kind of just want my GPS to tell me where I am. Okay. Each one of those rocks now, whether it's QOA or QLS or looking at the igneous rocks, every one of those rocks has a rock name. And you're like, oh no, more jargon. Every geologist literally walks up to a rock. We call this an outcrop. And we could probably write 3 pages about what we're seeing right here. We're capable of that. And then we put our nose to the rock. And when we put our nose to the rock, we look for patterns, we look for information. We're looking at both, we're looking here at megascopic observations, like what can I notice with my naked eye? Then we're going to take a sample of that rock and we're going to polish it, very much like a countertop polish. And then we're going to take a piece of that rock and we're going to glue it to a slide, a glass slide, and grind it down till it's thinner than a single human hair so that the light shines through it. And then we can put it on a microscope and we can look at what it looks like in a microscope, which we see here and here. So that's our microscopic observations. We can also take samples of that rock and put it in fancy machines and figure out what its chemical makeup is. And then we can name the rock. So the texture and mineral assemblage, as in first, what minerals are in here, and then how are they arranged? That's actually how we name a rock. So a rock's name is based on its mineral content, its chemistry, and the environment in which it formed. So every name, when I say something like gabbro or basalt or serpentine, that means something to a geologist. Gives 3-4 years of learning the names to understand what they mean. That's fair. And then when we look at formation names, essentially we're looking at groups of rocks that formed in the same environment. So we're just trying to make it a little easier to communicate with each other. Like saying Franciscan Formation or Sonoma Volcanics. Those are formation names. Now this rock, you might be looking at it and going, granite. Granite, I know. Granite is an igneous rock. An igneous rock could either be intrusive, which is going to be the pinky red colors on this map, or extrusive, which is going to be all of the orange colors on this map. Notice we have some orange through here. Don't even try to read all of the names on the screen. That was not my purpose today. It was instead like, I see words. And a geologist sees those words and there's a whole story. We could write 12-page papers on each one of these words. We have so much information in our brains about them. But when we look at this map of California, we're like, yes, there has been volcanic activity in the past. Some long ago, during the time of the dinosaurs, and some much, much more recently. So again, I'm not going to go over every rock name because I don't want people's heads to explode. But in the bottom right, you see where I put the star. That is tough, and it is in fact a tough rock. But more importantly, it was a volcanic rock that went boom, Mount St. Helens style. And then the ash rained down in this area. That's from Fairfield Osborne Preserve. That's a picture from Fairfield Osborne. That's part of the Sonoma Volcanics. But basalt is also part of Sonoma Volcanics. So even in something like a name like Sonoma Volcanics is not super clear. We need to be able to define that more specifically. And for those in Oregon and Washington, I just wanted you to note that this is green for this map. See, we don't agree with colors. All the green you see on this map, that's all volcanic rock. So you start to go, okay, we have a lot of volcanism in the Northwest. Then we have our sedimentary rocks, always telling us about surface environments. This is where we find most of our fossils. Geologists geek out over that. We can't help ourselves. This green stuff, that's our dinosaur age accretionary wedge. That's what was forming in that convergent boundary. All of this brown and yellow color, so these ones are much more recent sediments, broken rock pieces that ended up being compacted together to form sedimentary rocks. And then all of this buff color, these are sediments. They're not sedimentary rocks yet. Maybe someday they will become sedimentary rocks, but they're telling us about the environment now. And you see all these names here. And again, for every name, a geologist could write you a 12-page paper. Then we have our metamorphic rocks. All of the purple is going to be a combination of very old sedimentary and metamorphic rocks. And then this magenta color, which we see scattered about, is also metamorphic, specifically serpentine. And serpentine is going to form along convergent and divergent boundaries. So it's an important piece of the story as well. Just in case you were wondering, my favorite rock is blue schist, and you might understand why, because you're like pretty and sparkly. Also means there was a subduction zone. It's the only way blue schist can form is in a subduction zone. So we look at all of these rocks and you say, Nicole, you talk really fast and there's too much detail, and how am I ever going to know this?
Oh, Nicole, sorry. I just wanted to let you know that we are past the 30-minute mark, just as a reminder.
Perfect, thank you. I'm almost to the app here. I appreciate that one, Molly. So we have our rock cycle, which is interconnected with our tectonic and our water atmospheric cycle. And the reason we need this information, not only as geologists, but as humans in general, is we get to use these maps and all of this process information to help us prepare for living in the environment, for earthquakes and erosion, for landslides, the things that you kind of hope you know about ahead of time so you can prepare. We can use it to find soil types so we know where to grow food, highly important when you have 7.8 billion people on a planet. And we can use these maps to help us not only understand those more superficial environmental challenges, but also climate environmental challenges. If you want to know about climate, you have to know about geology. Geology quite literally is the record of past climate. Awesome. So now let's get to that map, to that app. This app, I have provided the instructions for on that website. Again, this is in the chat at the very, 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 very top of the chat so that you have a direct link that you can click on. If you don't have the app already, that's what you're going to do next, is you're going to get this app by going to rocked.org. If you have an iPhone, you go to the App Store. If you have an Android, you go to Google Play. Once you get the app, which looks like this, then you're going to open it and then choose how you want to sign in. I'm going to go with the sign in, like here. You just put in your name, email, password, normal, and then it's going to bring you to a tutorial. You are welcome to skip this introduction. However, I want you to be aware that where you see that kind of teardrop shape, that is a place where a geologist has added information. And where you see the arrow, that's where you are right there. The GPS you were hoping for that whole time. You now know where you are. Again, this image, if you're like, Nicole, you're going too fast, this image is on my website here, so you can go back to it. If you also get to the point where you're like, I really wish I had looked at that tutorial because I'm incredibly lost in this app, in the bottom right corner of your screen, there's a question mark. You can click on that, click on using rocks, click on tutorial, and you get right back to it. So at any time that you need to figure out how to use the app, it's built into it, which I really appreciate for this app. When it comes to navigating the app, what I find really helpful is that you open up on the map page and it tells you where you are, and then all you have to do is zoom in. So that's going to be your main function on this app, is really just go to the map. The paleo function is also awesome because it tells you how the plates have moved over the course of time. So it gives you a snapshot of what the Earth looked like during the time the rock you're standing on formed. And since, you know, there's so much chaos, we could use a little bit of help. So I have a 2-minute tutorial just to bring you through this. Say you are outside at one of our awesome regional parks and you see a rock and you're like, I want to know about this rock. A geologist looks at this and says, I see that this rock is oriented like this, and we draw symbols like this. Only a geologist knows what that means. We then take a picture of that rock. We go into the app and we choose checked in, and we add that picture to the app, and then we describe it in the same way that we would have seen it on a map. So as geologists, we're quite literally describing for each other what we're seeing and building more information into the app with time. Then you can go to the map portion. That's going to be your main portion. And for example, here I'm at Sonoma Mountain Regional Park. And here I'm in the green, that's Sonoma Volcanic. So I'm actually up there in the trees. And you just click on the green and you see all the stuff that Nicole already talked about, all that jargon, the source of that jargon, all the papers, awesome for geology students, massive amounts of information here. And then you can also, oops, I went too far, there we go. You can also use that information to say, well, what other rocks are present around me? Why, for example, when I look down this fence line, do I have trees to my left, but not to my right? Because 2 different kinds of rock. You also can use this to, for example, figure out the orientation of the rocks. You can use it to figure out fossils in the region. You can also use it to figure out minerals. I know, you're going, this is too much. I agree, it's a lot to do. So here's my suggestion. 1 second thing, there we go. Just go to the app, push map, and say, I am here. This is an image from Fairfield Osborne Preserve, which is awesome. And if you've ever been here, for those who've been to Fairfield Osborne and you're going up this path, you're in the Sonoma Volcanics. And maybe you've been at the top of Fairfield Osborne and you're like, why is it that there's trees up here and only in one place on the top of the mountain is there trees? You're like, what is this? Okay, I went there a month ago. The mud is disgusting. It's got the consistency of poop. So when you step on it, it like sticks to the bottom of your boot and it layers up like multiple inches. I can see from the smile, some of you are like, oh, I know exactly what that means. Well, that little node of trees on this app, you could say that's a different color right there. You click on it, it's a different rock. That's why trees are growing there, but not on the adjacent hilltop. So you can really use this to look at a lot of detail. So again, you're just going to get your app, click on map, and then we're going to simplify this. You are going to figure out where you are, map, figure out where you are, and then just put your finger down on the screen at whatever color you're looking at, and it will give you an image like what you're seeing on the right once you find that information. And this is what you're going to put in the chat. You're going to tell me where you are, like Washington State. And then from the app, you can tell us, well, what's the physiographic region, like coastal range? What's the age of the rocks? What's the lithology? and what's your stratigraphic unit. The map tells you everything. You don't actually need to go very deep into the map. So choose map, click on the rock color, and then tell me what you find. I am happy to take questions at this time if you are trying to figure out how to navigate the app. So you're welcome to either throw those in the chat box. Molly, let me know if there's any questions that are specific to how to use this app especially. It's only going to take, 3 to 5 minutes or so to do this information. If you don't want to add to the chat box, it's okay. You don't have to. I'm not going to force you. But if you have really interesting things to show me, then tell me. And if you are very, very lost, then tell Molly via the chat, and then she will tell me. Go be citizen scientists. Find out what rocks are in your backyard and beneath your feet. You can do so from your chair, by the way.
Wonderful. I was wondering, Nicole, if we should push the outside exploration or looking for rocks to 5 minutes instead of 10, since we're cutting close to the mark, and pushing the Q&A portion to after 2 p.m.
I think that will work perfectly. Yeah, I think that'll work.
Wonderful.
If anyone has any questions as far as like they're just having trouble navigating the app, now is a perfect time for that one. And I'm just going to look through some of these questions and answer them as we go too.
Yeah, so I guess just like with the very first step on the app, the first button I should hit so that I get off on the right foot.
So you're in the app. I'm going to assume that everyone got into the app. So once you're in the app, just click map.
Map, great.
And then zoom in. And you'll see, you're like, oh, my little blue arrow thingy is in this color. And then put your finger on the screen within that color. And then once you have that, you're like, ooh, that's a ton of information all about that one rock. Then you can use the upper left, you have that little caret, and you can return to the app, to the map. So you're like, okay, I now know I'm in the petaluma information. That's where the big stuff is. And then you just, once again, go back to your dashboard. So upper left, little caret, back to dashboard. And then that's where you're going to see the same information that you see on the right side of the screen. And that's what you're putting in. The rest of it, like the paleo, the fossils, the minerals, give yourself a couple years to figure that one out. I told all my geology friends about this app because I needed to make sure that it downloaded properly on everyone's phones and such, Android and such. The geeking out is extreme. It's really amazing. And every one of these like 20-year-long geologists are like, there's so much in this app. How do we make use of it? That's why I'm going to just simplify and say, use the map in the dashboard. It's enough. Nice. Okay.
Nicole, how do you get pictures? You said that you could bring up pictures of certain areas of check-ins.
The check-in is the picture that you take.
So how about to find out someone else's picture that they've done on a certain area? Like I want to see pictures that were done at Fairfield Osborne. How would I do that?
Perfect. Okay, so when you're in the map portion, I know it doesn't work very well for me to show people my phone via camera. It never does. But when you're in the map, you'll see in the bottom corner, there's the orange with the 3 stripes. You click on that and you toggle the check-ins so that the check-ins has the black bar next to it. And once you do that, it's going to come up on the map with a number of bubbles that have, for example, the numbers in them. And there's not a lot of them in this area because not a lot of people are actually using this app yet. It's relatively new. But as more geologists add more information to it, that's when we're going to start seeing those check-ins. So when I'm looking at this, I'm not really seeing much in the way of check-ins at this point, just because I don't think it's been used in this area all that much. I think if you went to Death Valley and such, you'd see quite a few more of those. Does that answer your question, Patty?
It answers it perfectly. Thank you very much.
I know every time I look at this, I'm like, more people, give me more information, please. But yeah, I haven't seen a lot of check-ins in this area. I think I might have been the first one to do a check-in in this area, also known as Super Nerd. I really find that this app is going to be most helpful for people to just go out into the world and say, I am here, and push on the screen and say, wow, the rock beneath my feet is an alluvial fan or volcanic rocks, and it's this age. So for example, one second, this is what I have found from where I am. To give you an example of what you could put in the chat, should you wish to. Ooh, nice, Diane. I'm on Sonoma Mountain, not too far from Fairfield Osborne, in the California Coast Ranges. So they're between 12 and 6 million years old. So this is essentially the sediment that got laid down on the last vestiges of the ocean before all of this rock got uplifted. It's sand and conglomerate and shale, so it's sedimentary rocks. We call it the Petaluma Formation, and the Petaluma Formation is essentially this transition from ocean to land. And what I find interesting is only a few million years ago, this was the edge of the ocean, and now it's an oak forest mountain slope. Like if I had a time machine, which I would love one, all I would have to do is go back 6+ million years ago, and I'd quite literally be on the edge of the ocean. I'd be on my own beach. And for those of us, which is everyone, who have been stuck inside, wouldn't that be awesome this last year if you had a time machine and you can be like, I'm just going to go back 7 million years. I'm going to be on my beach for a while. I'll return to the present when I wish to. Okay. Yes, David, if you are in Sebastopol, you can still check out Occidental. All you have to do is scroll to the location, like on your map, move to the location you're interested in and zoom in. The blue arrow is just going to tell you where you are at that moment, but you can explore anywhere you want in the world. That's one of the things that I think is most awesome. This is quite literally a worldwide map. You could bring this to Russia. You could bring this to Hawaii. You could go to Italy. You could go to Africa. You can do this anywhere you want in the world because it's actually a worldwide map, which, by the way, is incredibly difficult to find in general. Ooh, Lily, the Wilson Grove Formation is a really good one. There's fossils in that one, by the way. If you can find the little shell fossils, it is when the west side of Petaluma was a very shallow sea. Like much of it would have been shallow enough that you could have walked like thigh deep waters on the edges of it. Think of it as like almost tropical at that point. And Ellie in Montgomery Village area, yes, quaternary gravel. Essentially, the Montgomery Village area is the edge where the mountains meet the valley. And so it's where the rivers leave the mountains and flow into the valley and deposit all their sediment that they plucked from the mountains.
Wonderful.
Alluvial fans.
Oh, I said, and one of our other audience members, Kim's, asked if SSU has any equipment to make rock slides.
It does. SSU does have the equipment to make rock slides. I don't believe it is open to the public because the students use it all the time. By the way, it's not their favorite thing to do. If you would like to see a sad geology student, you go into the thin section lab. It's a very intense process. But the equipment is there for sure. Nice. That's a really good observation, Noel, that the geology is completely different on the other side of the Santa Rosa Creek, because it's common that a creek, and this is not all the time, but especially in fault country, creeks oftentimes will follow fault lines. They're following the point of weakness within the crust, and therefore what we see on one side versus the other can be different as a result. Not all rivers do that, but it's not completely unheard of.
Nicole, do you see how when we check in with our own map and we get all the dashboard that says that like whatever we are, California Coast Range, Neogenes, Shale, how about if I want to go and I want to place my pin in some place in Petaluma up in a hill? How can I get that same dashboard? Do I have to check into that dashboard, or is there a spot that allows me to have that same dashboard of another area?
Let's see. I believe that you actually have to either be in that area using your GPS, or you have to submit a check-in.
Thank you. That makes sense.
Yes. However, when you are in the app and you are in, hello app, 1 second, it got angry at me. I'm not surprised at it. When you are in the app in the map, and you just click on, for example, the rock, and you get the massive amount of information that is just a little too overwhelming. It tells you all the same stuff. It's just not in the dashboard appearance. It's still going to tell you the stratigraphic units, which is this one. And it tells you the description and the name of the rock and the age. So it's all still there. It's just not as clearly organized for the layman. It's more in like scientific speak.
This is so cool. This is going to be so fun to do iNaturalist and pull this out. This is awesome.
Yes. What I really recommend is when you're out in the field and you end up somewhere, you're like, why do the trees stop here? Like, what changed biologically? Stop, pull out the app, and see if you're on a fault line. And most of the time you will be, because the fault line will separate two different kinds of rock, and every rock has different ingredients. And every time those ingredients are going to support different kinds of ecosystems, plant communities. And therefore you're going to see that as part of the environment that you're observing.
It'll be fun to watch serpentine flowers, serpentine species, and how you can kind of map that out before. That's really cool.
It is. I love this. It's a lot though. But then again, geology is a lot. There's a reason it takes, maybe at least 10 years to truly understand what you're seeing from a geologic point of view. Molly, do you need to do your outro for the end of the hour, and then I can do all kinds of Q&A?
Yeah, that'd be wonderful. All right, thank you for everyone who's come. And just as we're wrapping up this event, hopefully you will feel more informed and empowered to take action with your geology research. Please make sure to, and just as a follow-up reminder, to make sure to enter your name in the chat so we can get an accurate record of who attended today's event. And please feel free to email our outreach leader, Carrie. I will put her email in the chat. If you have any other following questions after we sign off, either technical or any other questions about future events. And I also want to tell you about a few upcoming events the Center for Environmental Inquiry is having. This is just the third of the series in 19 virtual events that we're having this semester. You will find the full spring listings at our calendar, and I'll put the link in the chat as well for you to take a gander at. And remember that registration is required in order to receive the Zoom link and access the event. We are, here are the upcoming 3 events I want to highlight. On March 2nd is a deep dive in land management led by SSU Culture Resource student and our naturalist training TA, James Peterson. This is a follow-up to a really popular event last fall, but you don't have to have gone to the previous one to attend this one. And then on March 12th is our first live from the field event this semester, where we have an international collaboration event aimed at undergraduate classes, but it's open to everyone. They're made possible through the NSF grant for a project called the Virtual Field that you can learn more about in this link that I will post to the chat as well. There we go. And then the third upcoming event that I'd like to mention here is the on March 13th, and it's leading 3 separate events in collaboration with the North Bay Science Discovery Day. One event is a career panel in Spanish. Another is a local nature event about spiders, and the third is how young people with disabilities can help conservation efforts through nature photography. You can access the events at our calendar page. You can like spread the word because virtual events can be attended anywhere. So feel free to invite your friends and family if they live in a different time zone or country. Thanks again for all of you attending, and stay safe. We hope to see you again soon.
And I am happy to stick around and continue answering questions and comments on the chat as well. David Berman, I just wanted to note that yes, the Wilson Grove is definitely shallow sea, as in that entire formation formed in the shallow sea. As for your question about Russian River going through Petaluma, that is debated. I think it was likely, but it's hard to find evidence of that. And you can blame the San Andreas Fault system, not only for the current route of the Russian River, but for our general inability to understand how that has changed over time. This is what I think of, like, pretend you're gonna bake a cake and you're gonna put all the ingredients you need into the pot. Don't mix it up quite yet. You're almost there. So you're gonna add like the liquids and the solids. And then I just want you to take like a spoon and do this 3 times. So it's just mixed up enough that you're like, I'm not going to undo that. It's not gonna happen. Then I want you to take 2 forks and stick them in and do this. That's what the San Andreas Fault did. Now your job is to unravel that and separate all the ingredients out to the original ingredients before you added them to the bowl. Hence why geologists, let's put it this way, no one does their undergrad or their graduate work here because you'll never graduate, you'll never finish. It's just not gonna happen. You wait till like, not just postdoc, till you actually have a full-time teaching job or other than teaching job, and then you delve into the complexity of this. For example, David Barrow took over 10 years just to map the Tiburon Peninsula. That was just the Tiburon Peninsula. It's very complex. If you have questions, I'm also perfectly happy if either Molly wants to tell me those through the chat or if you want to unmute yourself. I love that, Cynthia. Perfect. Sitting upon clay. That clay expands and contracts, and a lot of the clay in this region actually does come from the volcanic rocks because there's so much feldspar in volcanic rocks and it breaks down into clay. It's one of the reasons that this is a very clay-rich region, in addition to its marine past.
Nicole, you
Yes.
mentioned the West Petaluma. What about the geology in East Petaluma? It just seems like very, it's almost like cement seeming when you get down digging into the soil. But that might not be, it might be just for these areas.
No, that's definitely true. There's a lot more Sonoma volcanics in that area. And what I didn't go into in this talk because it would just be too much was that, the Sonoma volcanics formed as a result, erupted as a result of the San Andreas Fault system, not subduction volcanism, but San Andreas Fault system volcanism.
Oh, is that, oh, okay.
Mm-hmm.
Were they, but they were more, it wasn't like actual volcanoes the way you think.
It was. It really was. All of the kinds. Like we're talking Hawaii to Mount St. Helens style. All of them. And that had probably occurred over, at least in this area, it's very hard to say 5-ish million years, maybe a little more or less. And all those rocks would have essentially been forming in volcanoes that would have been essentially poking out of this shallow sea as islands.
Oh, okay.
And then most of them would have eroded. So now you have like the sedimentary remains of them, the broken pieces of that once rock. And then you have to bury all of it. And then you're going to have to uplift all of it and then bury it with more sediment on top of it. And then you're going to also have to fault it.
Clear as mud. Yeah.
Yep. And so on the east side of Petaluma, what you're going to see is more Sonoma volcanics because the Rogers Creek Fault is more active. So it's uplifted that deeper Sonoma volcanics higher. So it's closer to the surface. There's more of it for us to walk upon. And then you have the rivers running down those steeper mountains into the valley and forming lots and lots of layers of sedimentary, like alluvial fans on top of and including pieces of the Sonoma volcanics. And because of the amount of clay in it, that makes it really hard. That's one of the reasons that you like described as like concrete to try to dig
exactly.
through.
Yeah. And
Nicole?
one related question about the Sonoma volcanics is that I've heard that Mount Burdell is the stump of an ancient volcano. That's just what people have told me. Is that related to the Sonoma volcanics, and is that true?
Yes and yes, and sort of and yes.
Okay.
So, okay, it is related to the Sonoma volcanics, but when we think of the San Andreas Fault, it started further south, think LA region, and then it's moved its way north in time. So it's propagating northward. And as it's done so, it's led to volcanism on its trek northward. But the Mount Burdell, actually, those rocks coincide with volcanic rocks that are found further south. And we think that the faults quite literally took that mountain, broke those rocks up, moved them in different directions. So they're now separated from each other, though they formed together.
Like in pinnacles?
In the Pinnacles area.
Oh, okay. Wow.
Yeah, so it's the rocks are actually just north of the Pinnacles, technically, not Pinnacles proper. But those erupted first and the Sonoma volcanics erupted later. So same process, different part of the timeline.
I see. So these volcanoes weren't underwater. They were actually sticking out of a shallow sea.
Yes.
Unlike other types of like the seafloor spreading type of volcanoes, which are underwater. Okay, thank you.
Believe me, the complication is intense.
Nicole?
Yes.
Yeah, hi, this is Ty. So my understanding is that the volcanism associated with the northern terminus, the San Andreas, occurred around 25 million years ago down in Southern California. And it has gotten progressively younger northward. By the time you get to the Pinnacles, it's around 8. And of course, by the time you get up here, it's as young as 2, or even recent volcanism in the vicinity of the geysers. And that's my understanding too, is that the volcanic rock was actually formed as a phenomenon associated with the slab window. In other words, as the San Andreas moves north, it's cutting off the subduction process and creating some kind of an environment that generates magma. Do you have any good source on exactly how that, from a physical standpoint, occurred?
Ooh, that's a good question. Well, I'll start with, I do have a number of geological articles and maps that are posted on my website, which I have up on the screen. It's on the same page that I provided previously, and I just provide direct links to geologic articles of interest. But to go to your question more specifically, I'll do my best to kind of describe how I see this in my mind. So we have the North American plate that we're standing upon. And long ago, the Farallon plate was going underneath the North American plate for subduction. Now, my other hand that's coming in and holding that plate, that paper, that's the Pacific plate. And as the Pacific plate meets up with the North American plate, they come together and the Farallon plate essentially just keeps subducting. I'm going to drop the paper now. Pretend that happened slower. And as it goes down, it essentially was going to break up the edges of that Farallon plate and expose a route around the edge of the Farallon plate. That would allow the magma from depth to come towards the surface. And then as the San Andreas Fault forms, I'm going to move my hands for this. As the San Andreas Fault starts to form, we have that same concept on the freeway of the cars moving towards each other and apart from each other. And whenever they kind of create that little apart from each other, that creates what we call a slab window through which that
Okay.
magma that's been generated is able to make it to the surface. So the volcanic rocks are actually coming up through faults,
Uh-huh.
which is actually more common than we realized, but we're only figuring that out in geology in the last 5 years, that faults are a major conduit for the magma. So
Well,
it is complicated, and we call it the slab window hypothesis, but the truth is no one truly understands it.
okay. Well, I know I didn't, so appreciate it. That's as good an explanation as I've ever seen.
I'll look on my website after this to make sure that there's a link to one article that I have found that's about the slab window hypothesis that I find helpful, as in it's focused on a little bit further north, but it does a really good job of kind of creating images that I think are more accessible.
Good, thanks.
Yeah. Any other questions?
Yeah, Nicole, I was wondering if you could just say a little bit about how all this stuff relates to environmental challenges and climate change, because that's what the center's all about.
Well, when we think about climate change, I'm teaching a geology of climate change class right now. It's I quite literally dream about climate change now. It's a little overwhelming. When we think of how we understand climate change, if our instrumental record to understand how weather and phenomenon on the surface of the earth progress, the rate of change only goes back to about 1850. We can go back to 5,500 years ago with our written history. So that gives us, at least some record, human derived record of change on the surface of the earth, but not with the same detail that we want it to be. So what we do is we use paleoproxy records. Fancy way to say we are going to look within the rocks for clues as to how change has occurred. We look at that chemically within isotopes, like isotopes of oxygen and carbon. We radiometrically date. We also technically just use sedimentary rocks, because every sedimentary rock forms in a unique environment. If you think of where do you find sand? You're like, well, I find sand on beaches, like river beaches and ocean beaches, but I also find it in the desert. You find sand in a number of places, but then how that sand layers up, how it's moved by wind and waves, what other stuff is built into that sand, like fossils, that's going to change over time based on that environment. And so we can use the clues, the structures within those rocks to say this rock layer formed in this environment. Now, for example, one of our famous rock layering is of a rock that we call diamosite, I can't even say it, diasmatite, which is a glacial moraine rock. It's formed by glaciers. And then directly on top of that, we find a rock called dolomite, which only forms in warm, shallow waters. So how do you get glacier-derived rock and then warm, shallow water? Sea level had to go up. And if sea level was going up, then the glaciers must have been melting. And if the glaciers were melting, the world was getting warmer. So we use those layers of rock to say, this is how the surface environment changed. And now that we know how the surface environment changed, we can say, this is how the climate had to change in order to parallel that change in rock environments. So we're quite literally using the rocks themselves as a proxy for understanding how the environment changed in any one location. But then we need to consider that we have to do this for billions of locations around the world over a course of 4.6 billion years. And we start to recognize the unfathomable complexity of climate on Earth and how it's always been changing. And the only record that we have of that change over the course of time is the rocks, the geologic materials that are left behind. So for understanding climate change, if we want to understand what's going to happen into our future, we look into the past and we say, well, when has this kind of event, technically in terms of greenhouse gases, abundant greenhouse gases suddenly filling the atmosphere, when has this happened before? And we go back far enough in time, we get to about 55 million years ago, and we see in the rock record a time when it was relatively cool, And then suddenly tons of greenhouse gases were added to the atmosphere over just a few thousand years. And then the world gets warmer. And we say, well, can we study this time 55 million years ago and first figure out where that greenhouse gases came from? And then say, well, how did the climate change? What were the changes that took place? How did the weather change? How did the ecosystem change? How did the plants and animals change as a result of that? And use that to help us understand what's going to happen into the future. Since the climate is changing, really, there's no question on that one. The climate is changing. Our real question is, how fast is it changing and what changes will take place and how is that going to affect humans? If we want to know about the future, we're going to have to look to the past to see what happened in the past as our only understanding of what might happen in the future. Carrie, are there other things you want me to add to that?
That was an amazing answer. Oh my goodness. Thank you.
My brain is a very scary place during a climate change class. I quite literally dream about paleo proxy records all night. Every night there's like ice cores in my brain. Yes.
Was the 55 million year ago event associated with the carbonate magmas, Kamchatka volcanism, and so forth?
I can't say that I know the answer to that because I haven't found any definitive focus on that. I'm actually going to be focusing on understanding that more over like mid-March. It's the PE, so the Paleocene-Eocene transition on the geologic time scale. More jargon. It's kind of the same thing as saying like May, June, Paleocene, Eocene. And what we do know is that we don't know exactly what the source of the greenhouse gases are, but we know that the greenhouse gases were released very quickly. And then we see a change in temperature. And that's actually opposite of what we normally see. And I think this is some of the newer information coming out about climate change. It's not technically new, we're just have a better understanding of it, is that through most of geologic history, temperatures go up and then greenhouse gases go up closely together, but temperature precedes greenhouse gases. So what's different about our current time in human generated greenhouse gases is that the gases happen first and then the temperature follows. So that's why we're looking at the PE or the Paleocene Eocene, because it's one of the few times in history we can say same order, what happens. I will look into that more. If you want to email me, you can easily email me through my website. And then when I find the relevant articles for that specific geologic time, I'd be happy to share them with you.
Okay, yeah, I had heard that there was a volcanic event in what is now the Kamchatka Peninsula, in which, for whatever reason, the magma was very carbonate rich and was thought to have exhaled a lot of CO2 into the atmosphere. But I don't know if it was at that particular point in time or some other one.
Yeah, I'm not sure about that one either, but I also know the massive volcanic eruptions, the Siberian traps that erupted 250 million years ago had a very similar situation where the rocks that they were erupting through included limestone, which is a lot of calcium, carbon, oxygen. So as that magma went through that carbon-rich rock, it was more carbon dioxide rich than normal and led to really, really high CO2 levels.
Yeah, okay.
As in, it was already bad, just makes a bad thing worse.
Right.
Good question. I'm going to look into that one more. That's lecture 12, working on that one.
Okay.
Does anyone have other questions?
Yes, I believe Jessica wrote in the chat, do rocks give you information about where water is currently being stored in the Earth's crust, and such as aquifers?
Yes. Okay, so an aquifer is a layer of sediment or any other kind of rock within which water can flow and be extracted by humans. So for example, every single rock layer technically bears water. All of them do, but we're human and we're egocentric. We can't help ourselves. That's just the way our brains are built. We define an aquifer based on our ability to usefully extract water from that layer of rock below. So when we're looking at usable water and therefore layers of rock through which we can extract that usable water, we're looking at how does that water flow through that rock or that sediment layer? What are the chemical makeup of that rock? How fast can it flow? And for example, if we're talking about granite, which is going to be a lot of the Rocky Mountains, there's a lot of uranium in that. So that's going to break down into radon, which has radon gases. And then we have all kinds of water problems associated with that on a chemical level. So when we're really looking at hydrogeology, the flow of water through the rock, we're interested in rate of flow. Is it flowing between sediments or within cracks? And how is that changing the chemistry of that water? And how usable is it? So for example, if we use so much water from an aquifer that there's just not enough left, that we cannot usefully extract it anymore, it's technically not an aquifer anymore. It's only an aquifer when we can use it. Did that answer your question? I think so.
Thank you.
Mhm. I hear a very rhythmic sound. Is that the beginning of someone wanting to ask a question?
I just muted somebody so I'm sorry, Anita, if you wanted to talk, please go ahead. I think that noise was coming from you.
It happens. There's all kinds of weird things that happen.
I did have a question. It sounds so awful myself.
Yeah, you have some kind of feedback happening. Do you want to put your question in the chat and then I can just read it? Ooh,
I did.
Okay. Can you recommend a map that a novice geologist living in Sonoma County can understand? Rocked. The app is your best bet because every geologic map you get, it's going to be large and have a lot of information in it. And the thing is that you then have to be like, well, I'm looking at Sonoma volcanics. And then you have to go online and be like, what are Sonoma volcanics, and do the research. And that's one of the best things about this app, is just put everything in one place. So you don't have to go beyond the app to have most of your questions answered. And if you do have more questions, the app actually gives you the source of information, the scientific papers. So you know exactly which papers to go to look for that information, if you want to, in which case the geology speak is going to get pretty intense. Ooh, and I think that I may have answered your question. If I didn't, go ahead and add in.
I see a
there's
question from Anita that she typed in about 20 minutes ago. It said, we have had a series of small earthquakes this past year here. Does the Rock app have a way of linking to that data? Does the geology recorded in well drilling logs go into this database? Kind of two questions there.
Good question. I do not think the well drilling logs go into this database. This is much more superficial. And there is no active like earthquake portion to this specific app. There are, for example, I'm looking for my earthquake one. There are several of them. I recommend everyone has the app called My Shake, as in like My Shake. It's a turquoise color with like white dots and lines on it. And that is a app that is the equivalent of our early warning system. Now, it does not predict an earthquake. There's nothing that predicts earthquakes at this point. We don't have that knowledge yet. What it does do is say an earthquake has already been detected and sends out warning signals, and the sound waves that are sending the warning signals move faster than the earthquake waves do. So if you're in a good location relative to the epicenter of that earthquake, you might get a warning through the app that the earthquake has already started. That might give you a few seconds to a few minutes to get to a safer place, as in not in a building, which is why I think it's so helpful for us in California that we would, it's our best bet at ever having warning that an earthquake is already occurring. But if you are interested in knowing about earthquakes that have occurred, there are a number of different apps called Quake Feed and Quake Alert, Earthquake. I kind of use all of them because I don't love any of them specifically. The shake map, my shake, does actually have a list of recent earthquakes as well. And you can contribute your information, as in your experience of an earthquake, relative within that app as well. But no, the Rocked app does not include active earthquake information. I think it already does so much that it might be too overwhelming if it added more.
Eric has a question. He said, he wrote in the chat, how worried should we be about methane being released by the defrosting permafrost?
Very. Sorry. Just being super realistic here. When we think of, well, methane, number one, is going to be we call it a stronger greenhouse gas because it quite literally absorbs more heat. So it's going to hold on to more heat. And there's a massive amount of methane in permafrost. And so as the permafrost thaws, that methane that's been trapped in within that solid layer, it's going to be released into the atmosphere where it can capture the heat and increase the rate at which the atmosphere warms, which increases the rate at which the oceans warm, which increases the rate at which the glaciers melt. All it does is increase the rate at which things are already happening. And it's already happening much too fast, like way, way, way too fast. So yes, we should be more than just a little concerned about the methane that is melting out of the permafrost. So for example, in the Siberian area, the Siberian tundra, there are areas where the permafrost has melted so quickly that it's causing massive surface cave-ins. Like huge holes are developing in the surface of the earth because it's melting underneath and then the surface is falling into those caves. In addition, especially like I'm using Siberia only because I have direct pictures of this in my head. There's also a lot of coal layers from times before the glacial ice stage that was fairly recent, when there were large forests in that area, and then those forests died and they became part of the sedimentary rocks. And that carbon is essentially coal-like that has been stored underneath other layers of sedimentary. And you're like, good, carbon stored, all is good. Until someone, very rarely nature, more likely humans, accidentally causes that deep layer of carbon to start burning. Yikes. Now we have underground coal fires. And you're like, oh, it's Siberia. It gets to like -30. It'll be fine. They'll just go out. They don't. They keep burning all winter long, regardless of what the surface temperature is. So that methane is very much part of the biological layers within the sedimentary buildup. And not only is the methane being released, but there's also a lot of carbon material that's also releasing carbon, in addition to an increasing amount of carbon-rich layers that are burning uncontrolled. Not only in Siberia, but also almost everywhere in the world. China is going to have some of the most. Pennsylvania has quite a few. So yeah, I am very concerned about the methane that is thawing, but climate change, there's a whole list in my head about the things I'm concerned about. Now, just to kind of, spin that one just a little bit, climate is always changing. There's no such thing as no climate change. The climate will change regardless of whether or not we are here. What we can do is use our knowledge of the past to say, this is how the climate has changed in the past. This is what we expect for the near future and prepare accordingly. We can use our knowledge of the past to be prepared for an inevitable change of the future. But we can also use our knowledge of the present, our current scientific knowledge, to say, well, we could slow down the rate of change if we change the way we're interacting with the environment. That's where our power lies. We don't get to stop the change. Our power lies in having some control over our actions and how they relate to the rate of change. Change is not a bad thing. It's just, when change happens really fast, nobody's happy. Hence, March of 2020. I wanted to answer David Berman's question too. Blue schist is quite literally a piece of the oceanic plate that got buried beyond about the 10-mile mark, changed into pretty shiny minerals, And then for reasons we don't understand, chunks of it get brought back up to the surface. It's literally a chunk of the oceanic crust that almost melted, but didn't quite. Other questions? Yeah. More than happy to answer many a question. If you are overwhelmed and just want more and more geology, you're like, all I'm going to have to do for the rest of my life is learn more geology to understand this, then definitely check out my website, because I am leading tours essentially at local parks to talk about the local geology. I'm doing it in very small groups because I am highly aware there's a pandemic and I'm not going to mess with that. Limiting it to 5 people at a time and just kind of sporadically doing these tours. And that's a great form in which to really try to understand the geology around you and to ask a lot of these very detailed questions. If anyone has any more questions, I'm still here.
Well, this has been really wonderful. Let's see, we're gonna have to say goodbye. Everyone. Thanks again for such an engaging conversation, Nicole, and to everyone for an amazing questions. We hope to see you in another event soon.
Thank you, everyone. Feel free to email me with more questions should you have them, but thank you for joining me. I appreciate it.